Okay, so let's look at the register movement instruction. Okay, there are few instruction for the register movement instructions. Okay, before we go more details on the register movement instruction, okay, let's look at this data, how the data processing instruction works. Okay, so the data processing, okay, will include the move, arithmetic, logical, compare, and multiply operation. So every time we use the data processing means that, okay, either you're going to move a data, okay, from one memory to a register, or from one register to another register, or you're going to do the arithmetic operation. Okay, the arithmetic operation includes addition, subtraction, division, or multiplication. And sometimes, okay, you're going to do a logical function. So that's why it's one of the data processing. Okay, this logical functions such as the exclusive or, and, not, or, and etc. Okay, so all operation except multiply instruction are carried out in ALU. Okay, so this is your, okay, by looking at this one here. Okay, so you have a register bank, and then you have your ALU, and you, so here, okay, all of the data processing will be done inside of ALU except the multiply. Okay, so actually, okay, the ARM has a 3 address format. Okay, so we have RD, okay, which is your destination, RN, okay, which is this is your source register. Okay, and from here, this source register, the data from the source register will directly use as your first operand. Okay, and then we have the RM, which is another source register. And this RM here, you can apply a barrel shifter, which is a function unit such as you're going to the do a data bit shifting to the right or to the left. Okay, you can do it the barrel shifter here, and after that it will go to the ALU as a second operand. Okay, for the barrel shifter here, okay, you can see the CPSR, the control program sensor register, okay, will determine either, and the flag will be updated. Okay, so data processing instruction do not access a memory. Okay, so if you see here, every time you do a data processing, it only involved in the register bank. Okay, not involved, not accessing the data memory. Okay, only register bank is used in order to do a data processing. Okay, so do not access memory. And instruction operate on two 32-bit operand, which is will produce a 32-bit result. Okay, means that, okay, you have two source, Rn, which is the size is 32-bit, Rm another 32-bit, okay, and then you do the ALU, and the result of this ALU is 32-bit as well. Okay, and instruction can be pre-processed operand to using a barrel shifter. So this barrel shifter, it means that you're going to do to manipulate your value or your data from this RM register. Either you're going to shift it to the left, shift it to the right, and etc. There is a few barrel shifter instruction that you can use, okay, before it will go to the ALU. Okay, and this is the syntax of the data processing. Okay, first you have the operations. Okay, OP stand for operation, followed by the S. Okay, which is this S here is your suffix. If you're going to check, okay, if you're going to tell the CPU to update your APSR, okay, application program status register, so you need to put this S after your operation here or your mnemonics here. And then you have the RD, which is a destination register. Operand 1, okay, this is your RN. Okay, so this is your RN. And operand 2 is your Rn. So this is your Rd. Okay, so this first operand, okay, actually is a register, can be from the register or can be an immediate value. Meanwhile, for the operand 2, this is a flexible second operand. Why it is we call it as a flexible second operand? Because in the in this operand number 2, okay, you will undergo to this barrel shifter here. So this is the things, okay, that you can do inside of the barrel shifter. Either you're going to make it as an immediate value, or the value is coming from Rm, okay, your register, or you're going to do these things here, okay, by putting it to the barrel shifter, you're going to do the logical shift left, or arithmetic shift right, or rotate right. Okay, so this is the things that you can do for the second operand. So that's why we call it as a flexible second operand. Okay, so this operand 2 can be an immediate value, register, or a value that you already manipulated by using the barrel shifter operation. Okay, so this is the barrel shifter operation. Okay, this thing here. Okay, so again, so before you do the sum data processing, okay, you need to have a two operands. Okay, the first operand is either from your immediate data or from your register, and the second operand is another source register, but it will undergo a barrel shifter, and then after that you do the data processing, and it will produce a results. Okay, so let's look at the first instruction here. Okay, for the data processing. Okay, now we're going to look at the data movement. Okay, so the instruction for the data movement includes MOV, okay, which is it stands as to move a 32-bit value into a register. So every time you use the MOV means that you're going to move from a value from one register to another register. Okay, meanwhile for the MVN, okay, so this is a move the not of 32-bit value into a register. Okay, means that you complement the value from the first register, okay, complement the value, and copy the complemented value and put it to another register. So that is what MVN do. Okay, so the register movement are classified as a data processing instruction. Okay, so it involves to of the register to register data movement, and it is always 32 bits size. Okay, so we have a few examples here. Okay, let's look at this example. MOV R0 R1. Okay, assume that your R0 is this value and R1 is this value. Okay, so after you did this first instruction here, what happened here is your R0, okay, so since you, okay, so this is instruction MOV R0 R1, you know that you're going to move value from R1 and put it to R0. So what happened here, R0 will have this value 1, 2, 3, 4, 5, 6, 7, and 8. And what about your R1? R1 value is remain or unchanged. Okay, what about this one here? MOV R1 R0. So now what happened here? You're going to take the value from R0 and put it to R1. Okay, so that's why you see here the R1 equal to this value, okay, which is you copy the value from R0 and the R0 unchanged. Okay, assume that, okay, we assume that this instruction here is not executed as it's not executed sequentially. All right, means that the first instruction and the second instruction not dependent from one to another. So this is an independent instruction. Okay, if this instruction here is dependent, okay, from one to another, means that, okay, you need to take an updated value lah, okay, after you do the second instruction. Okay, for this case here, okay, if let's say lah, okay, this task here, this instruction is sequentially executed. Okay, executed. Okay, what happened here is, okay, for the second instruction here, okay, after you do the MOV R1 R0, so R0 will have this value. Okay, so R0 will have 1, 2, 3, 4, 5, 6, and 8. And after you did this instruction, so now R1 will have the same value of R0. This is only for when the instruction is executed sequentially. But in this case here, in this example, we assume that, okay, this instruction is independent, okay, means that it is not executed sequentially executed. Okay, for the third instruction, MVN R1 R0. So what happened here is, okay, what you're going to do here is you're going to do the, okay, find the complements of R0. Okay, since your R0 is 0, 0, 0, 1, 1, 1, so 0, 0, 0, 0, 1, 1, 1, 1. Okay, if you complement this one here, 0, you will get F. What about 1? What would be the value? Okay, since this is a hex up, okay, so what you need to do here is you need to change to binary dahulu lah. Okay, you need to change to binary value first. So the binary value for 1 is 1 lah. And after that, you do the first complement. Okay, and you will get this value here. So this value is actually equal to E. So that's why the value is F, 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 E, 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 and takes the value and put it to R1. So this is what the MVN do. Okay, move the knot of 32-bit value into a register. Okay, so this is for the registered movement. Okay, next. Okay, we can use this MOV instruction, okay, to load a small constant into the register. Okay, so the ARM instruction are fixed length. Okay, since the ARM instruction is a fixed length, so no single ARM instruction can load a 32-bit immediate value into a register. Okay, means that you cannot simply load 32-bit number to your register. Okay, to your general purpose register by using a MOV instruction. Okay, so the constant can only be 8-bit number. Okay, by using the immediate value, you can only put 8-bit number to your GPR by using a MOV. Okay, so what happened here? If you can see here, MOV R0, and this is the immediate value. Okay, so what happened here? You're going to put 0 to R0. Okay, so since what we call here, MOV can only support 8-bit number. So what about if you're going to load a 32-bit number to your register? Okay, so to do that, you need to use another instruction. Okay, you cannot use a MOV instruction to load a value more than 8-bit to your register. Okay, so these examples here. Okay, we have another example. So immediate, and by using the immediate addressing mode, okay, you already learned about this in the previous class. Okay, so MOV R0 hashtag 100. So every time you came across with this hashtag symbol, you know that this is an immediate value. Okay, so what happened here is you're going to move value hundreds to R0. Okay, since this value 100 here doesn't have any symbol in front, so you know that this belong to decimal number. Okay, if you have something like this, hashtag 0x20, for example, so you know that this is a hexadecimal. You have hashtag 0b01101, so you know that this belong to binary number. Okay, but this one doesn't have any symbol in front of the values or in front of the number, so you know that this belong to decimal number. Okay, since 100 is less than 8-bit, okay, for the 8-bit data, for unsigned number, the maximum value is 11111111. This is equivalent to 255. Okay, so you need to very careful lah. Okay, for unsigned number, okay, the maximum number is 111111, which is 200. 55 in decimal. Since this is 100, so you can simply load this value to your R0. So what happens if I put something like this? MOV R0 hashtag 300. Can you do that? You cannot. Okay, why? Because 300 is greater than 255 is greater than 8-bit. So you cannot load this value to R0 because MOV to load the value to your register by using MOV instruction, the value must be 8-bit data only. Okay, so this is what happened lah inside of your memories. Okay, so this is actually a program memory. Okay, in which first, okay, your let's say lah this instruction here MOV R0 hashtag 100 is located at this address 000264 inside of your program memory. Okay, so what happened here? The CPU will go to this address and takes the instruction. So this is instruction. After it be decoded, actually this is your instruction, and this is the instruction after it decode to machine code. So what happened here? Okay, the CPU know that okay now you're going to load this value 100 and put it to R0. So after you execute this line here, value hundreds, okay, will be stored inside R0. Of course lah, you need to change the 100 to hexadecimal value first. Okay, then after that you can store it to R0. Why? Because R0, the value inside of your register always hexadecimal numbers. Okay, so in order to move a constant greater than 8-bit, so what you're going to do? Okay, we can use the LDR instruction. Okay, so if you're going to move a constant with a 32-bit number, 16-bit number, okay, 24-bit number, you can use the LDR. This instruction here, LDR equal, okay, which is this is a pseudo instruction. So assembler will generate the optimal sequence of MOV, MVN, or other from the literal pool. So label can be used as a constant to implement absolute address to refer outside the current section. Okay, so this is an example. All right, so you have a LDR R0 equal to OXFF, means that this is a 8-bit data. You're going to put it to R0. Or you have a 32-bit data. Okay, you can simply write LDR R0 equal to OXFFF 43FF and put it to R0. Okay, so this is the coding that you can use in assembly language. But when the compiler do the disassembly, so this is what happened lah. Okay, it will disassembler to this coding here. It will automatically disassembler to this coding. Okay. Okay, so again, okay, just for the reminder, okay, so every time you're going to load a value to a register that is a bigger than 8-bit, okay, you can use this instruction here, okay, LDR, and then followed by what register that you're going to put, and equal, and after that equal to the value that you're going to put to that register. Okay, so now we're going to load addresses. Okay, how to load addresses to your registers. Okay, so to load an address, the ADR pre-studio instruction is commonly used. So this ADR calculates an address PC relative and move it into the destination register. Okay, so this ADR is replaced with ADDR0 PC and hashtag offset in the assembly. Okay, so instead of using an ADR, okay, you can use the LDR in order to what we call here, in order to load an address to the register. Okay, later on we will see more details on how this LDR and LDR works. Okay, next is a time to approach to immediate. Okay, since that okay, you're going to move a 32-bit data, but okay, you're going to use a MOV instruction. Okay, since the MOV only support 8-bit data, so what happened here is there is a time to approach in order to move a 32-bit data by using the MOVW and MOVT. Okay, so this is the instruction here. If you can see MOVT, which is move 16-bit constant into top half of the register, and MOVW move another 60-bit constant into the bottom half of register. So this is what happened. You see RD, okay, bit 31 to bit 16, okay, equal to upper 16, and RD bit 15 to bit 0 equal to lower 0. Okay, so let's look at this example here. Okay, in order to move a large binary number, okay, so what happened here, you can break it into by using this instruction here. Okay, so first MOVWR01. Okay, so what happened here is you're going to move this value here, okay, the 16-bit value to your R0, and this is for the bottom half lah of your register, and MOVTR0 hashtag 1. So what happened here is you're going to move another 16-bit number to this R0. Okay, for example, okay, I give you an example. Okay, so you're going to load this value. Okay, so this is a 32-bit data. Okay, you're going to load this value to R0. Okay, how to do that? Okay, the simple way to do is okay, we have two way to do this. Okay, the first way here is by using the LDR. Okay, R0 equal to 0x, okay, 1 2 3 4 A B C D. Okay, so this is the first uh solution lah, okay, to put this value to your R0. Okay, the second solution, okay, you can use this instruction, okay, to put this value, 32-bit value, to R0. How to do that? Okay, first, MOVW, okay, R0. Okay, since MOVW is for the bottom half, okay, so you need to take the 16-bit of the bottom half. Okay, so this is the lower half lah. Okay, and then this is the height. This is the top half. Okay, so you take this lower, okay, 2 bytes here, put it to R0 by using the MOVW, okay, which is 0, sorry, kena ada hashtag. Okay, since this is an immediate value, so you can simply write hashtags 0x A, B, C, D. So what happened to your R0? So your bottom half of R0 will have this value, and then MOVT R0 with hashtag take the top half here OX1, 2, 3, 4. And after you execute these two lines here, your R0 will have this value 1, 2, 3, 4, A, B, C, and D. Okay, so the first solution here, okay, only needs one line of instruction. Okay, but the second solution need to have two lines of the instruction. Okay, so this is how you're going to move a data from one register to another register by using the MOV instructions. Okay, any question up until here? Okay, if no question, then we move to the general data processing instruction. Okay, so first let's look at the arithmetic instruction. So arithmetic is actually a operation that includes the addition, subtraction, okay, and sometimes multiplication and etc. Okay, so this instruction perform a binary arithmetic on two 32-bit operands. Okay, you have a few instructions here for the arithmetic instruction. Okay, one is a ADC. Okay, so what this ADC do? You're going to add two 32-bit values or and with a carry. Okay, so this is what happened lah. RD equal to Rn plus with n plus with your carry. Okay, if you have a ADD is to add two 32 bits value. So RD equal to Rn plus n. N is your Rm lah actually. And for RSB, so this is a reverse subtract to 32-bit value and carry. So this is the operation here. RD equal to n minus Rn. And RSC is a reverse subtract with a carry to 32-bit value and a carry. So this is what happened here. N minus with Rn minus with a carry. Okay, and then SBB is a subtract with a carry. So this is what happens. Subtract RD equal to Rn minus n minus C. So you look at these two things here. Okay, one is a reverse and one is a simply direct subtract. Okay, you see here. So this one here, n minus with n, but this one here is Rn minus n. So that is the only difference between the RSB and SBB. Okay, either you're going to subtract Rm with Rn or Rn with Rm. Okay, then we have the SUB. Okay, so this SUB used to subtract 232 value without, okay, so this one here, please correct without a carry, okay, with no carries. Okay, so RD equal to RD minus N or RD minus Rn. Okay, every time you do these arithmetic instructions, so what happened here, okay, your status register will be updated accordingly. Okay, if you put the suffix s lah. Okay, so if you put this something like this, okay, you do ADC and ADCS. Okay, what are the different? Okay, both do the addition to value with a carry, but one so ADC here. Okay, the first one here. Okay, no status register update after you execute this line. But if you have put the S, the suffix S, what happened here is your flag register will be updated. Okay. So this is the flag register that will be affected every time you do the arithmetic operation. Okay, which is we have the N, Z, C, and V. So this flag register here is located at your application status, application process status register, APSR. Okay, located inside of your APSR. Okay, so previously we already know that. Okay, N belong to N negative flags, Z will belong to 0 flags, C is a carry flags, and V is a overflow. Okay, so every time you see the sign bit, okay, of your value is 1, so this end flag will automatically set to 1. Okay, and every time you do the arithmetic and it produces zeros, so what happens here, the Z flag will be set. Okay, and if you have a carry, if you do the addition or subtraction and have a carry, okay, between your most significant bit, okay, then what happens here, the carry flag will be set. And meanwhile, for the V, okay, so this is for overflow. So how to determine the V flag? Okay, you can look at this. Okay, you can look at this, what we call here, cases here. Okay, the V is set to 1 in either of two cases. Okay, the first case, okay, if you have a carry from bit 30 to bit 31, but no carry out from bit 31. Okay, contoh, examples. Okay, so this is a bit 30 and this is a bit 31. If you add these numbers here, sorry. Okay, so we add this bit here. 1 plus 1, you get 0. And you have a carry there from bit 30 to bit 31. Okay, and produce 1. Okay, so what happened here is the V equal to 1. Why V equal to 1? Because you have a carry from bit 30 to bit 31. And at the same time, there is no carry from 31 to this bit here. Okay, so the V equal to 1. Okay, and the second case, there is a carry from D3 out to C1, but no carry from D30 to D31. Okay, we have another example here. So this is bit 31 and this is bit 30. Okay, you plus this number here. So what happened? 0 plus 0 is 0. And then 1 plus 1 is 0 and 1. Okay, you see you have a carry flag from this bit to this bit. Okay, but there is no carry from 30 bit 30 to bit 31, so V sama dengan equal to 1. And what happened if you have something like this? Okay, you have, okay, so this is bit 30 and this is bit 31. Okay, you add this bit here, 1 plus 1, you have a carry from 30 to 31. Yes, you have carry, 1 plus 1, and you have another carry. So what happened to your V? V will automatically become 0. Why? Because first you have a carry from this bit to bit 31, and from bit 31, then you have another carry. So what happened? V automatically equal to 0. Okay, so look at this description here. Okay. Okay, the overflow flag is low, okay, which is equal to 0 if there is a carry from both D30 to D31 and from D31 out. Okay, so this is how you're going to determine the V flag, the overflow flag, by looking at bit 30 and 31 as well as the carry from 31 and out. Okay, so this is the difference between a carry and overflow. Okay, so you can look it by yourself, this one. Okay, so let's look at this flags exercise. Okay, we are supposed to have a R0 equal to this number, R1 this number, R2 is the number, and the initial value of N, Z, C, and V is 0, 0, 0, 0. Okay, you're going to find the value of the flags after each instruction. And okay, this is the most important thing. Assume each instruction runs independently. Okay, means that the first instruction and second instruction are not dependent from one to another. Okay, so let's look at the first. Sorry. Okay, so let's look at this first instruction here. ADD R3 R0 R2. What happened here? Anyone can help me? What this instruction do? R3 equal to R0 plus with R2. Okay, what is your R0 value? Okay, your R0 is this value, OXFFFFFFF. And then you're going to add with R2, which is 0, 0, 0, 0. Okay, so your R3 equal to, after you add this number here, will be F, 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 F. So this is your R3. Okay, now we're going to look at this flex here. Okay, N flex. What is the value of your N flex? Is it 1 or 0?
0.
Okay, N flex is 0 or 1?
Okay. 0.
Okay, one of your friends says that 0. Okay, how to determine the this N flex here? Okay, first you look at this bit here. Okay, you have 32 bit number. Okay, you look at this. Okay, this number here is F. If you change it to what we call here binary, okay, F equal to 1111. Okay, so this is a bit 31, bit 32, sorry, 30, 29, and 28. Okay, to determine the N flex, okay, you need to look at this bit here, bit 31. Okay, your sign bit, either it is 1 or 0. Okay, look back at this one here. Okay, in the previous class, we already learned about this thing here. Okay, so first, okay, you by looking at this result here, okay, you need to look at the bit 31. Okay, since the bit 31 is 1, consists of 1, so 1 means negative. Okay, so what happened? So N sama dengan equal to 1. What about your Z? Z is 1 or 0?
1.
Z is 1. Why you telling the Z is 1? Okay, what is the Z flag indicate of? Okay, what this Z flag telling you?
Result is 0 or not.
Okay, when every time, okay, you do a arithmetic operation, or you arithmetic of data processing, and the result is 0, okay, then after that the Z equal to 1. Since now, okay, after you add this number here, okay, you have a value inside of R3. So the Z will be 0. Okay, so that is how to determine the Z flag. Okay, looking at the value inside your register. If the value is 0, okay, no value, then Z equal to 1. Okay, if the value is non-zero, which is you have a value inside of your register, then after that, the Z equal to 0. Okay, what about the carry flags? Okay, carry flag. How to determine the carry flag? Okay, to determine the carry flag is you need to look at the bit 31 lah. Is it any carry from 31 to out? Okay, 31 to bit 32, which is the outside bit. Is it any carry? No, because you add with 0. Okay, 0, 0, 0. Okay, you have this one, 1, 1, 1, 1, 1, 1, 1, 1, and then this is until 32 bit lah. Okay, plus with 0, 0, 0, 0, 0, 0, 0, 0, and then after you add, you produce the same number. Okay, this is your bit 31. Okay, is there any carry from here? Bit 31 to bit 32? No carry, right? Because 1 plus 0, you still get 1. So no carry, so C equal to 0. What about your V flag? Is it 1 or no? Okay, how to determine the Z flag? Okay, the Z flag, you need to look at bit 30. Is there any carry from bit 30 to bit 31? Okay, since after you add this number here, there is no carry. Okay, and is that any carry from bit 31 to bit 32? Okay, no carry as well. So what happened here? V sama dengan equal to 0. Okay, so this is the first result. Okay, before that, I'm sorry. Okay, since this one, I forgot to mention you. Since this is a ADD. Okay, so ADD. Okay, the answer for this one here is always 0, 0, 0, 0. Even though you see the n fact is 1. Okay, why? Why is that? Okay, because this one doesn't have the suffix s. Okay, so no suffix s means that you don't want to update this flags here. Okay, so that's why the value is 0, 0, 0, and 0. What about the down here? ADDS R3 R0 R2, which is similar to this one, but this one, the difference is this one got S, the suffix symbol here. Okay, then for this one here, okay, after you do the execute this line here, okay, the result still the same. Okay, we should get this value. Okay, sorry. Okay, so this is 1, 0, 0, and 0. Okay, let's I put another instruction. ADDS R3 R0 and R1. So what happened? What is your n flags? Okay, before that, what is the result? R3. What is your R3? After you add this number here. R0 plus with R1. Okay, so this is your R0 and this is your R1. So what will be the value? Anyone?
Zero.
Okay, the value will be 0. Okay, correct. So 0, 0, 0, 0, 0, 0, 0, 0. Okay, now we look at this Z. Yeah? Okay, since there is 0 value inside of R3, then your Z flag automatically become 1. Okay, because no value inside R3. Okay, what about your N flags? Is it 1 or 0? Okay, N flag, you need to look at bit 31, correct? Okay, since your bit 31, okay, this one here, okay, which is 0, 0, 0, 0. So this is bit 31. Since your bit 31 is 0, so you put a 0 lah to your N flag. What about your C?
Zero.
Okay, your C, is it your C is 0 or 1? Okay, because you plus this number here. F, 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 plus with 1.
This one.
Okay, so that is a carry. Okay, after, so you have 32-bit number. Okay, you change it to hexadecimal. Sorry, binary. 1, 1, 1, 1. Okay. Okay, and then this is 1, 1, 1, 1. Okay, so this is 1, 0, 1, 2, 3. And this is 31, 30, 29, and 28. Okay, and then you're going to plus with 1. Okay, so what happened here? 1 plus 1, you will get 0, and then you have a carry. 1 plus 1, you get 0, carry 0, 0, and this one will Okay, and then you
But
have carry there.
Doctor, it depends. It depends on signed number or unsigned number.
Okay, so this one here, okay, let's assume this is a unsigned number, but again, okay, it will the negative here will depend on the bit 31.
Okay.
All right, the value of n is depend on the bit 31. Either is a 0 or 1. Okay, now, so we have 1 plus 1, you get 1, 0, and then you have 1 plus 1, you get 0, and you have a carry. So here, you have a C equal to 1. What about V? V is 0 or 1? Okay, so in this case here, your V is 0. Why 0? Okay, since carry you have C is equal to 1, and here from bit 30 to bit 31 as well, you have the carry bits here. Okay, what the V flag telling you? Okay, only okay, it's telling you that the overflow flag is low if there is a carry from both D30 to D31 as well as the D31 to out. Since both here have a carry, okay, from 30 to 31 you have a carry here, and 31 to out you have another carry, so automatically V equal to 0. Okay, so this is how to determine the N, Z, C, and V flags after you perform a arithmetic operation. Okay, so next we have the logical instruction. Right, so this is a few logical instruction available in ARM assembly language. Okay, the first one here is a and D. Okay, what this A and D do? Okay, you're going to do a logical bitwise AND of two 32-bit values. Okay, means that you're going to do the logical AND between one register, one source register with another source register. Okay, so this is the same operation lah. RD equal to R and do the logical AND with an AND. And ORR is a logical bitwise OR of two 32-bits number, okay, which is you're going to do the logical OR between one register with another register. So this is the operation RD equal to RN, okay, then logical OR with N. Then you have a EOR, which is exclusive OR, okay. So this is the operation RD equal to RN do exclusive OR with your another registers. And BIC stand for logical bit clear. Okay, means that you do the logical AND. After you do the logical AND, then you do the complement. Okay, you get the not of that logical AND. So this is the instruction. Okay. This is the command. Okay, which is you do the logical AND, and after that you not the results. Okay, so I think we stop here. Tomorrow we'll continue with this shift and rotate instruction. Any question up until here?